This is a very common problem for radioactive decay. So you're given a differential equation, Q prime, in this case it's equal to negative 3Q, and it says determine the half-life. So the half-life is going to depend on the K value here, the rate, the proportionality constant for the radioactive decay, and we have to figure out how to do it. All right, so first thing we're going to do is we're going to solve the differential equation. And let's go ahead and do that here. So it ends up being Q of t. You can do the separation of variables, and it is Q naught times e to the negative 3t. In general, you just write it's negative kt. Alright, so now we got to figure out the half-life. So what does the half-life mean? It means how long do you have to wait until the amount of radioactive substance decreases to half of its value. Alright, so we know that Q at time 0 is equal to Q naught. We were given that. And essentially we want to find Q at time tau, this Greek letter, is equal to 1/2 of Q naught. That's what we need to solve. Well, okay, so Q at tau, the half-life, is equal to 1/2 Q naught. Well, I can plug in tau into this equation here. It's Q naught times e to the negative 3, and then plugging in tau for t, it's negative 3 tau. Now I've got this equation, 1/2 Q naught is equal to Q naught e to the negative 3 tau. Alright, first thing to do is probably just to divide both sides by Q naught, so we end up with 1/2 equals e to the negative 3 tau. Alright, next sensible thing to do, what if we take the natural log of both sides? So natural log of 1/2 is equal to natural log of e to the negative 3 tau. Alright, well the natural log of e, those kind of cancel out, and the ln 1/2, I'll leave that alone. So we have ln of 1/2 equals negative 3 tau. Alright, and I do want to simplify this a little if I can. So the ln of 1/2, that's the same as ln of 2 to the negative 1 power, equals negative 3 tau. And so I can take that exponent out, so this is going to be negative 1 times the ln of 2, natural log of 2, equals negative 3 tau. And then I can actually cancel both the negative signs, so I have natural log of 2 equals 3 tau. And then I can solve for tau by dividing by 3. So tau is equal to natural log of 2 over 3. Alright, and that turns out to be approximately 0.231. So whatever radioactive substance this is, maybe this T is measured in years. It's decaying fairly rapidly, and radioactive substances can decay, I think some of them less than a second, and some of them can take tens of thousands of years or more. Alright, now if you just want a formula for this, the half-life, if you have this equation, so let me write it out again. If you have Q prime equals negative K Q, then the half-life tau is always going to be the natural log of 2 over K. And one thing to note here, doing this check here, when I looked at the natural log of 2 over 3, I wanted to make sure the whole thing was positive, because we should have a positive amount of time should have to elapse in order for this radioactive substance to decay up to half of its current value. So this number was positive, so it looks like we did it right.